Power factor is an indicator of the amount of power that's wasted when delivering power to a load, which makes it an extremely important parameter in AC power delivery. In this video, we'll talk some more about power factor and how to correct the power factor to improve power transmission. Power factors and power factor correction are best understood in terms of complex power. So let's review the main concepts there first. Complex power is represented as S. In rectangular form, it consists of a real part, P, and an imaginary part, Q. P is the average power. It's the product of the RMS voltage times the RMS current times the cosine of the phase difference between voltage and current. Its units are watts. Q is the reactive power. It's the product of the RMS voltage and the RMS current times the sine of the voltage phase angle minus the current phase angle. Its units are volt amps reactive, or VAR. The complex, average, and reactive powers are easily represented graphically as a power triangle. S is this point here in the complex plane. On the power triangle, it's represented in polar form as an arrow with a length equal to the magnitude of S and an angle, theta V minus theta I, from the positive real axis. The average power is the real part of the complex number. It's an arrow in the direction of the real axis. The reactive power is in the direction of the imaginary axis, since it's the imaginary part of the complex power. I briefly introduced power factor in a previous video, but now let's talk about it in some more detail and give it some physical significance. The power factor is commonly abbreviated as PF, and it's unitless. As I already noted, power factor is defined as the cosine of the voltage phase angle minus the current phase angle. Keep in mind that the voltage and the current are not independent. They're related through the impedance of the load. So if I have a load with some voltage and some current, the load impedance is defined as the ratio of the voltage phasor to the current phasor. That means that the angle of the impedance is equal to the angle of the voltage phasor minus the angle of the current phasor. So the phase angle difference in the power factor is just the phase angle of the load impedance. Now let's talk about why power factor is important in power delivery from a generator to a load. Unless theta V minus theta I is 0, there will be some reactive power component. A lower power factor corresponds to a higher reactive power. The reactive power, Q, doesn't perform work. The load just stores the reactive power and returns it back to the generator. So it's just being traded back and forth between the load and the generator. So if the power factor is low, there will be a correspondingly larger amount of power that's being sent to the load, but not being used for anything. This means that extra current and voltage is being provided to the load, but the load doesn't do anything with that power. So the power company is sending you extra power, which you just give back to them, and they can't really charge you for that. The problem with this, from the power company's point of view, is that it isn't actually free for them to send you power. If this is the power company's generator and this is your factory that's consuming power, there's always a transmission line between the generator and the load. This transmission line will have some resistance, so power will be dissipated during the transmission process. The power company is spending money to send power to you that you're just sending back to them again. Understandably, they don't like this, so they may require you to improve your power factor. In order to reduce the wasted energy associated with transferring reactive power, the power company may require users, especially larger ones like factories, to maintain some minimum power factor. For example, the power company could tell you that if your power factor isn't at least 0.9, they just won't send you power anymore. If your power factor is too low, you may need to correct the power factor to meet the power company's requirements. Under certain circumstances, which are actually pretty common, this is fairly easy to do. Most large loads are inductive. For example, in a factory, any large motors will look like inductors. These types of loads cause a lagging power factor. If you have a low power factor and the power factor is lagging, adding a capacitor in parallel with the load will tend to increase the power factor. Before I do a numerical example, let's go into a little bit more detail about the overall power factor correction process. Suppose I have a generator that's providing voltage to an inductive load with impedance Z sub L. The complex power delivered by the generator is S1, and it has a power factor of the cosine of theta 1 here. The average power delivered to the load is P, and the reactive power is Q1. I want to change the load so that the power factor is now the cosine of theta 2. I still want to deliver the same average power, since average power corresponds to the useful work done, and I want to keep doing the same work. I just want to lower the reactive power so that the power factor is increased. The reactive power corresponding to the desired power factor is Q2, and the new complex power that gives the average power P and Q2 is S2. I can change the complex power by adding a capacitor in parallel with the load. Now the load impedance and the capacitor can trade power back and forth rather than sending it back to the generator. The capacitor will be chosen so that the reactive power introduced by the capacitor, Q sub C, changes the total reactive power from Q1 to Q2. Mathematically, Q2 will be Q1 minus QC. Now let's do a simple numerical example to see how this works. In this circuit, the voltage V sub S of t is 100 times the cosine of 377t. We want to check the power factor on this circuit and then redesign the circuit if necessary to get a power factor of 1. In order to redesign the circuit to change the power factor, we first need to analyze the circuit as it is. To determining the existing complex power, we first convert the circuit to the frequency domain. This is the frequency domain circuit. I'll need to find the source current first. Then I can determine the complex power delivered by the source, which will give me everything else that I need to know. The equivalent impedance of the load, Z sub L, is the product of these two impedances, 100 times J377 ohms, over the sum of the two impedances, 100 plus J377 ohms. If I convert this impedance to polar form, Z sub L is about 96.7 at an angle of 14.9 degrees ohms. The current, I sub S, is this voltage, 100 at an angle of 0 degrees, over the load impedance, 96.7 at an angle of 14.9 degrees, which turns out to be about 1.03 at an angle of minus 14.9 degrees. The power factor, PF, is just the cosine of the voltage phase angle, 0 degrees, minus the current phase angle, which is minus 14.9 degrees. That's the cosine of 14.9 degrees, which is about 0.97. This is lagging. Finally, let's check the load reactive power, Q sub L. Q sub L is the voltage magnitude, 100, times the current magnitude, 1.03, over 2, times the cosine of theta V minus theta I, which we've already decided is 14.9 degrees. This turns out to be about 13.3 VAR. The power factor of this circuit is about 0.97. We want to increase that to 1. We can do that by adding a capacitor in parallel with the load such that the added reactive power due to the capacitor exactly cancels out this 13.3 VAR. This is the circuit with the added capacitor in parallel with the load. We want to choose the capacitance C that will exactly cancel the 13.3 VAR reactive power of the original circuit. So we want Q sub C to be the negative of our Q sub L, which is negative 13.3 VAR. The capacitor power, Q sub C, is equal to the capacitor RMS voltage times the capacitor's RMS current times the sine of the phase difference between voltage and current, which for a capacitor is always minus 90 degrees. This becomes VRMS times IRMS is VRMS over the magnitude of this impedance, 1 over 377C. Sine of minus 90 is minus 1. So this becomes VRMS squared times 377C times negative 1 is negative 13.3 var. VRMS is 100 over root 2, the voltage level divided by root 2, times 377C is equal to 13.3. If I solve this for C, C is equal to 7 microfarads. That will give us a power factor of 1. Our example of power factor correction was extremely simple since the capacitor voltage difference was known. In a more realistic case, when there are elements between the capacitor and the generator, the calculations get a lot more complicated, although the general idea remains the same.